the integral relatively easy. Once you have this normalization constant, you have to update the posterior approximation, Q, and you update the parameters of Q using these formulas for the Gaussian that I showed in the slides. Basically, you have that Q is given here. You have a MJ is going to be MJ is the mean of the titled distribution, which is MJ/I plus the variance of the titled, and then the derivative of the log of the normalization constant with respect to the mean of the titled. This is the update for the mean, and the update for the variance is similar. These are just the formulas I have in slide 15. I'm just applying those formulas. This is the update for the mean and the variance of the posterior distribution. And once I have these updates for the mean and the variance of the posterior, I have to refine the approximate factor. So I just compute. I'm going to erase this. The final step is to compute to update the approximate factor, which is the same as the ratio of Q nu. This is we are getting Q nu here, and we update the approximate factor as the ratio of the new posterior and the titled. And I make use simple. I just have to make use of the quotient rule of Gaussians to get finally the parameter for the approximate factor, which is going to be The update is going to be just the ratio of Gaussians, which is just the variance of the ratio is the inverse variance of the ratio is the difference of the inverse variances, and the mean times the inverse variance of the ratio is the difference of the means times the inverse variances. And finally, we have to update this constant, Sj, so that this thing is satisfied. So I don't know exactly the exact formula for this, but it should be easy to do. You just have to do it would be the integral. It would be the normalization constant of these two Gaussians times set I, the value of sorry, this is Sj. Okay, and this would be the EP algorithm for probit regression. You just for probit regression using a factorized approximation to the posterior. You iterate this until all the factors converge, and you get an approximation to the posterior. Yes. This one? Yeah. Yes, so these are the parameters of the posterior. M and V are the parameters of the posterior.
So in this formula there should be a J?
Yes, you can, it depends on the value of the index. Yes.
Okay.
Yes, so here I was using different indexes to avoid confusion with because I'm refining the ith parameter and this the ith factor. I'm refining the ith factor and this is the jth parameter. Yes.
Should there be a yi?
Here? Yes, I missed. So it would be here. Yes. So this would be multiplied by yi. Yes.
So when we are iteratively refining f I hat, we have to compute cavity distributions, and to compute the cavity distribution we have to compute
the titled distribution, which is
many means
this one.
I don't know for every other node.
What do you mean?
Well, basically, I want to compute define the fi hat. Then I have to compute.
Yes, you have to
both j or both n variances and means, right? For all the j's. Right?
Yeah, you have to do that for all the parameters. Yes.
For all the parameters.
Yes. And the steps are computing the cavity. It gives you d. Yes, this is all for j1 to d, and in this case it is the same for j1 to d, and this here also también. So the steps are to refine the ith approximate factor. I compute the cavity by extracting that factor from the posterior, computing this ratio. It gives me these parameters for the cavity distribution. Then I compute the normalization constant of the titled distribution, which is the product of the exact factor and the cavity. I get this formula. Once I have this analytic expression for the normalization constant, I can update the parameters of the new posterior to match the mean and the variance of the title distribution. I do this by applying these formulas. And then once I have updated the posterior, I have to update my approximate factor. Basically, in this posterior represents the product of all the approximate factors and my approximate factor updated. But I don't know the value of that approximate factor because it's hidden in the product of all the approximate factors. So I have to extract the contribution of that approximate factor. And I do that by just computing the ratio, which gives me these parameters for the approximate factor. So what problems may happen when you implement this in practice? As I mentioned, it may happen that some of the variances of these approximate factors are negative. It turns out that that might be a problem Well, I guess as long as this thing is positive, it's fine. If you had like a huge negative variance, maybe that could be a problem. So when you run EP, you will have to verify that all the updates are possible. Because of these negative variances, maybe sometimes you won't be able to do the update. For example, if I had here a huge negative variance, this would involve computing the square root of a negative number, and I wouldn't be able to work with that. So in that case, when that happens, you basically don't refine the factor. To refine the factor, you would have to compute that thing, which is not possible, so you just ignore that factor and you refine the next one. And hope that in the next iteration you might be able to refine the factor, and maybe it may happen that you are not able to refine the factor anymore, and then you just stop. And that factor is not optimal, but you expect it to be good enough.
I have a question. So when we say iterate refining Fi hat, so then we have to compute the cavity distributions, compute Zi, then we have to update. It's still part of refining the factor Fi.
Yes, yes.
And the final step for the factor Fi.
The final step is this, yes, this is the final step for the factor Fi. So this would be the operations in the loop of EP that goes through all the factors.
And then we have to pick different factor, Fi plus 1, and we have to do all the steps,
yes,
including the update.
Yes, yes.
If you select an obtain a negative variance, I assume that can happen also as you're finishing with the algorithm?
Sorry?
Can you also be left with a negative variance when you finish iterating the algorithm?
Yeah, that might happen, and that's another thing that can happen. Usually it doesn't happen most of the times, but it may happen. So if you get some negative variances, you don't care much as long as so the factors, the approximate factors, can have negative variances. But because you are interested in the posterior approximation, which is the product of all the approximate factors, if the variance of the posterior is still positive, assuming that even though some of the variances in the approximate factors are negative, you don't care much about that. It may happen that one of the variances is so negative that the posterior produces a negative, you get a negative variance in the posterior. In that case, basically you don't do the update of that factor. So whenever you get to this stage and you say my variance is negative, you forget about updating that factor, and you don't complete the update.
I would like to thank you, Jose,
Thank
for
you.
your lectures. It was very nice, and we learned a lot. And we'll meet again the next Monday at 9, as usual. So hopefully I will see you again. Thank you.
Okay.
Thank you.